Okay, so we have discussed about partition function briefly in one of the previous videos. So today we'll talk about partition function for the system with energy degeneracy and this relationship between the partition function and other thermodynamic quantities of a system. For example, the relation between the partition function z, which is we have defined here, we have written here. So z with respect to like how it's related to the entropy and then enthalpy. This is H is enthalpy, total energy, pressure, specific heat at constant volume. Okay, so we will see as we go along the video. Okay, so first let's discuss about the partition function for the system with energy degeneracy. So now consider assembly of an ideal gas molecules, okay, obeying classical statistics. So classical means, so we consider these particles, they obey so these are classical particles, okay. Moreover, we can, let's say we can distinguish the particle from one to the another. Okay, so we know from the earlier Boltzmann canonical distribution law, which is also called as Maxwell-Boltzmann distribution law, that Ni, which is the number of particle in the ith cell, is equal to GIA e to the power beta e, where beta is given by 1 by kt, which we are familiar with. So A is the constant which we have discussed earlier, and Gi is the degeneracy, or is the number of cells in a zone. If you remember from the earlier lecture, which are having nearly similar energy. Okay, so Gi is the number of cells in a zone which are having nearly same energy. So in fact, this is the degeneracy. Okay, so Gi is the energy degeneracy of the system. All right, so how do I write then? So to proceed, so earlier as well, so we know that the sum of Ni give you the total number of energy, right? So that's how we can write for this expression as well. So if I substitute this Ni in this back here, so I will get this GIA e to the power beta e. This is Ni, okay, and this A is constant. Okay, so A will come out, then sum over Gi minus E beta, which is equal to N, and this particular expression, so this is N by A, so I take this A to the right hand side and I can write, and this is sum over to this sum over all i's. Okay, so I have not written in the other ones, so e to the power beta e. So this particular expression is the partition function for z, which is the partition function for the system with Gi degeneracy. Okay, so that's what it is written here. Yes, so same thing is being written here. Yes, this is a partition function for, so this expression we will be using very regularly as we go along the course. Okay, so this is one expression for partition function with for the system having energy degeneracy. Okay, so degeneracy is here Gi. All right, so now let's look at the relation between the partition function and entropy. Okay, now again from the earlier lecture, we know that the entropy is related to W. W is the thermodynamic probability. Okay, so this is the number of microstates for a given macro state is given by this entropy, Boltzmann entropy relation. Okay, so and S equal to K ln W. Now for a classical system, again, so this we are familiar with total number of particle. So in a system is, let's say, capital N, and there are, you know, so many cells within that, or we can think about the compartments and cells. All this concept we are, by now I think we are very familiar with. So this Ni is the number of particles or the molecules in ith cell, okay, and this W is the number of microstates corresponding to a given macrostate, or in short it is thermodynamic probability. Okay, so if I take log of this thermodynamic probability expression, okay, W, so this also we have derived in one of the earlier videos. Okay, this expression for W that is written here. Okay, so this pi, the how the sum is, it represents, you know, sum of each term. Okay, so this summation expression here, the W, this pi represents product of each expression. Okay, so if I take since this is a very large number, this n, and that to n itself is a very large number, if we take factorial, it's going to be even bigger. So all the mathematics we go with by taking logarithm. Okay, so that's why to deal with this expression with the help of mathematics, so we take log on both sides. Okay, natural log on the both sides. So that's why we get ln W. See here, this is product. Okay, so this part is product. So ln n factorial plus, because the ln a into b, so that expression will go. Okay, so that formula is being used here. Ln a into b is ln a plus ln b. So then you get here as, you know, n, so the numerator part you see, so the ni ln gi, okay, minus, because this is divided by ni, so you get this minus ln ni factorial. Then again we had introduced this approximation in the earlier expression as well, though the Stirling approximation, where your ln n factorial can be it's like, you know, when this n is very large number, its factorial can be approximated using this expression. Ln n factorial is equal to n ln n minus n. So let's use this Stirling approximation for this particular term and wherever there is this factorial. Okay, so these two terms, and substitute back here. Okay, so this n ln n factorial will be giving to n ln n, this capital N here, like minus n. So this term will remain as it is, whereas here again you, after substitution for this ln n factorial, ni ln ni, this is minus, then minus minus or plus, so then ln ni. Okay, let's see how what happens. All right, so if you take this, then again you substitute for this ni, because ni using the Boltzmann distribution law, which we had discussed earlier as well. So we have derived this expression in earlier lecture. So where this gi, as I said, this is represents the energy degeneracy, right? So, and you substitute for this ni in this expression. Okay, here you will see why. So you can actually, we can substitute anywhere, but just to, you know, mathematically to carry out the simplest steps going forward. So I have not done anything. See, this is the same expression in the previous slide as well. So this is the expression. Okay, you can start. This is just copy and being pasted here. This is the same expression here. Okay, and then substitute for ni. So when I substitute for ni, so I will just replace this ni with this. Then you take log, meaning ln of this expression. So other terms are same. This is whatever these are same. So here ni is again common here, ln gi minus, see, ln gi. So this is ln ni into ln a, and then you take, so this is, there are three terms being multiplied here. Okay, so then the from the ln ne of beta e will give you negative beta e, right? So with multiplication of ni, but this negative and this so this negative and this negative will give me plus. So plus ni beta e, and then you have sum of ni. Okay, so now you will see some terms will get cancelled out. Okay, so if you have to think about, let's say, so yes, so this particular term and this particular term will get cancelled out. Okay, so we'll remain with, moreover this ln a can be taken common. Okay, let's see in the next one. Yes, so so this part remains same. So this sum over ln ni, this is beta e plus n. Okay, so here what you need to be a little careful, this is beta is constant here, beta is constant, right? So that can be taken, so I'm just talking about this particular term. Okay, so here sum over I and I, this is what, so you are trying to, it's like Ni is number of particles in the ith cell having energy Ei. So if I sum up all such terms, will give me the total energy of the system. So this will give me the total energy, which is E, isn't it? Okay, and then sum of this is Ni will give me N, this is total number of the particles. Okay, so let's substitute for that. So I will be having, so that's why I have beta E here. Okay, and then the sum of Ni will give me the capital N, total number. Okay, so which is this N, negative N, and this positive N will get cancelled again. Okay, it will become 0. So I'll remain with n ln n minus, so this expression I will remain with. Again this sum of Ni here in this term will give me the capital N. Yes, so then I'll remain with this n ln n by a beta e. Now this n by a is what is partition function, because just you go back to earlier slide. Okay, just now you have written, see this part, this is z, this is nothing but partition function. Okay, so n by a is your partition function. So I will be having this ln w here. Okay, is n ln z beta e. Okay, so substituting this ln w back into this entropy expression or the Boltzmann entropy relation, then sk ln w will give me what, simple ln w, just substitute. Okay, so I had this expression n ln z beta e. So substituting here I will get whatever meaning expression that we have, this one. Okay, so k ln so kn ln z plus k is both like constant here, beta e. Okay, and so the beta, if you substitute back the 1 by kt multiplied by e, then this k will get cancelled out, and then I will have this expression. Okay, k ln. Okay, so this is expression for energy. Sorry, so this is the expression for the entropy. Okay, entropy, and so this is a relation which shows between the entropy of the system and the partition function. It has also the total energy and temperature associated with this. So this expression includes these terms. Okay, and for ideal gas, we know that for ideal gas, if there is n particles, so so it has got 3n degrees of freedom. In the previous videos, video when we had discussed about the equipartition of energy, there we have discussed about this term. So the total energy is given by 3n into half kT. So that's why 3 by 2 n kT the total energy. So I can substitute for this energy, this term energy, so by this expression for ideal gas, and while doing so E is being replaced by 3 by T n kT. So the T and this temperature down the T will get cancelled out, and I will remain with this. So for so relation of entropy with partition function, okay, for ideal gas is given by this particular formula. Okay, so now let's look for the relation between Helmholtz free energy, which I represent here by F, and partition function. Okay, so for that if you remember from earlier thermodynamics, the Helmholtz free energy is given by this total energy minus Ts, where T is temperature, S is entropy. Then substitute for the expression entropy just that we had derived now. Okay, so by substituting that, we are remain, so E and E will get cancelled out. I'll remain with this minus nkt ln z. Okay, this is Helmholtz free energy. Okay, this is one of the simplest expression that you can derive if you know what is the expression for entropy and partition function. Okay, so next, the relation between total energy E and partition function. Okay, so the average, so if you consider the system with n particles, okay, so the average energy we can calculate, it's like total energy by total number of particles. So this is average energy of a system having n particles. Okay, so given by this particle, and then you expand it, so by sum over all the particles in all the cells divided by the total number of, or the number of particles in each cell. So then what do? You substitute for the Ni using the Maxwell-Boltzmann distribution law, or the Boltzmann canonical distribution law, where Ni is given by this Gi A e to the power beta E. Okay, and then multiplied by E. This is just, you follow the simple mathematics here, right? So I have just rearranged the E, got it forward, and so the A is constant in the denominator as well as in the numerator, so that will get cancelled out. So I will remain with this, and you know that the denominator is nothing but your partition function. Okay, so your average energy is related by this particular expression. Okay, so now what I will do, I need to do a little bit of extra mathematics, where the partition function is given by this particular expression, beta is 1 by kt, and then for isothermal isochoric transformation, or for that kind of process, so I do del z by del t at constant volume. So volume is constant here, so you just need to, so the expression, this one, you need to differentiate with respect to temperature, keeping volume constant, and then I'll be getting this particular expression. Okay, and follow up. Okay, so I will this so the k and t square is constant of summation, so I can take common, and then I will remain with this particular expression. Okay, so if I take this kt square to the left hand side, I will have this, and then again this. So this particular expression, so this one, so this is with the green, so this part was in the numerator of this expression, so this is same expression. Okay, so if I do that, substitute for this expression. Okay, so this was, so if I, from here I can write this numerator sum over I gi ei e to the power beta ei, so this is equal to what? Z E bar, or the average energy for this purpose, right? So then I will be having, so that's why I have in the, on the right hand side, Z and E bar. Okay, so the average energy here is given by this expression. Okay, and the total energy of the system is what? So average energy multiplied by total number of particles. So I have got the expression here for the average energy, this particular expression, kt square by z, and then del z by del t at constant volume. Okay, so I multiplied by total number of particle n, so I will remain with this expression. So this is the relation between the total energy and the partition function. Okay, then let's look at the relation between the partition function and enthalpy H. So the enthalpy of the system is given by H equal to total energy plus PV. P is the pressure, V is the volume. So for ideal gas, PV equal to, let's say nRT, let's assume for our simplicity n is equal to 1. Okay, so that's how we have PV equal to RT here, and you substitute for E. Just now we have derived the total energy E, this expression, and then plus RT. Okay, so this is gives you the relation between the partition function and enthalpy, right? So this is quite simple. Okay, so just let me just sort of highlight this part. Okay, this is your H, this is enthalpy. Okay, so next we will see the relation between the Gibbs potential, okay, which is dependent on G here, then the partition function, and Gibbs potential energy, or the Gibbs potential function is given by this enthalpy minus Ts. T is the temperature, S is the entropy. Then I substitute all the expression that we know already. So H we have derived, S we have derived, substitute all of them, then some terms will get cancelled out. Okay, and then okay, so here is this E, substitute for again this total energy expression that we have got. Okay, and then it will be remain this RT minus ln KT ln Z. Okay, so here you can slowly carry out the maths and see. Okay, this is nothing very serious maths. It's simple addition, subtraction, differentiation. Okay, so next, the relation between pressure and partition function Z. Okay, so the pressure, we know that from the earlier thermodynamic studies, is the pressure is given by negative del F by del V at constant temperature. This F is here the Helmholtz free energy, and this F was so F is given by, so if we go back to that expression, so Helmholtz free energy with partition function, this expression is given by this minus nkt ln Z, and so if we substitute back here, so the F here is minus nkt ln Z. Okay, so if I substitute back, so the negative will get it will become positive, and so nkt ln Z by del ln Z by del V at constant temperature. Next, we look at the relation between specific heat at constant volume with the partition function Z. So the specific heat at constant volume is Cv, is given by this particular expression del E by del T at constant volume. So we already derived the expression for the total energy. Substitute here and then carry out the partial differentiation. Okay, and then we get this particular expression. Okay, so this expression we get it.